So let's just consider an ordinary differential equation, right? I have dw dt equal to minus lambda times w. But then I add an error term on top of this ordinary differential equation. How much does that error term matter? Right? The error term, let's figure out how much does that error term matter for three cases. One case is lambda equal to 0. So if lambda equal to 0, then there are two cases. One is without tau, we get a w is equal to a constant, right? With tau, w equal to the same constant as the initial condition plus an integral of tau dt. That's a classical case of just accumulating. The error you have added on the right-hand side of the equation, which is very similar to the truncation error we are introducing, just accumulates. The longer you integrate, the bigger the error, because the more tau has gone into the solution, right? Now, another case, lambda less than 0. Okay, so then without tau, w is equal to e to the minus lambda t, right, times the same constant. And with tau, does the error still accumulate indefinitely? Is it still like in the first case, where as t goes to infinity, the amount of error I have in the solution goes to infinity? It's no longer the case, right? Whatever error I introduce, they actually decays with the solution. I mean, easy case to see is that if I introduce tau periodically, like every time instant, every time step, the error introduced in the beginning, after a long while, has decayed to 0, and only the most recent error introduced actually matters, right? So my w prime minus w is actually, you can prove, is actually bounded. Okay, I mean there is actually an analytical form of this, right? So w prime is actually equal to this plus integral of 0 to t of tau times exponential of minus lambda t minus t prime dt prime. I mean, you can. Math is complicated, but like the intuition is that it stays bounded. Previous error gets decayed. The third case is when lambda is greater than 0. The error you introduce, even if the initial solution w is equal to 0, right? Even if initial solution is equal to, this should be plus, right? So the lambda less than 0 means, actually means, right, lambda less than 0 actually means it's a decaying solution. Lambda greater than 0, it's a growing solution. So the tau means w prime minus w is going to grow exponentially. So the error I introduced, even if I just introduce one small error at one time point, the error is going to amplify. It's not just going to accumulate, but amplify. So these three cases are the three possible situations you have when you're looking at the difference between analytical and numerical solutions. Okay, either the error just stays there, accumulate, or the error is actually going to be stabilized by the numerical scheme, or the error is going to amplify. And the case I just showed you is that in both cases, the error gets decayed. It's a decaying, it's a stable numerical scheme. It's just for the higher frequency oscillation, the equations are more stable than the k equal to 1 case. And therefore, even though you are introducing more error, the resulting error in the solution is actually less. All right, so we'll study more of this on Friday in building 3. All right.